Hello, everyone. Welcome to this session where we'll be discussing using ManeFrame II for research and teaching. I'm joined here with Eric Godat, and we'll be covering kind of the basics of HPC and what it is and how to use M2 specifically, just a brief introduction, and then followed by a demo of our new open on-demand portal for accessing M2 resources. So I always like to talk about how SMU has a fairly long HPC history that goes way back to the mid-50s. So in the mid-50s, they had the UNIVAC Computing Center, and it housed UNIVAC 120, which you can kind of see there in the back left. It ran off of punch cards and had a magnetic tape storage. So completely different type of computing than we have today. But nevertheless, SMU has been at the forefront of supercomputing, certainly at a liberal arts university. So what is high-performance computing? High-performance computing is the use of computing resources that are significantly more powerful than what's commonly available. As such, it's always a moving target. This is my unofficial definition of what HPC is. Essentially, everyone's cell phone, their laptop was the world's fastest computer, if you go back far enough, right? So what you can do with a computer or an HPC environment is dependent upon how you could use those resources and what kind of problem you're trying to solve. And so hopefully we'll be able to talk a little bit about how your applications can fit and run on M2. Okay, so the type of HPC system that we have here at SMU is called a cluster. And a cluster is a collection of individual computers. So these are just standard kind of off-the-shelf server-grade hardware. And we call these nodes. And each node has different levels of compute resources associated with them. In this case, I'm showing 2 CPUs per node, which the vast majority of M2 is this setup where you have 2 CPUs per node. And then, of course, each of these CPUs has lots of cores, significantly more than 4 today. But nevertheless, the goal is to have your application use as many of these resources as possible in order to efficiently execute your code. Okay, so let's look at some examples of HPC applications. So first we'll look at tornado forecasting, followed by structural analysis and drug design and ray tracing. These are all applications that are not specific to research being done here at SMU, but are kind of examples showing the parallelization that is required to really take advantage of M2's resources. So tornado forecasting. So the goal here is to predict where and when tornadoes may form, right? And so the faster you can predict where a tornado might form, the sooner that you can turn on the sirens, which gives people more time to seek shelter, right? And so this is a unique HPC application because it's being fed basically ground truth data in real time and has to run its simulation as fast as it can so that it can make predictions literally as the storms are passing overhead, right? And so data is fed into the model in real time, such as radar temperature, humidity, wind speed, things like that. Right? So the way they do this is they divide the atmosphere into blocks. It's basically a grid, a regular grid with very high columns. And the computational cost of solving an individual square within this grid scales with the humidity. So basically, if the air is drier, it's more easy to find the solution. And then as it's the more humid, so where it's raining, it's more computationally intensive to find the solution. And obviously, better predictions come with smaller blocks. The more fine-grained you can be, the better your prediction will be. But obviously, this comes at the cost of scaling the computational cost associated with the simulation. So another example is structural analysis. Finite element analysis is a very commonly used tool for analyzing three-dimensional structures. And so you basically take your 3D object and decompose it into a mesh. And you can see here that the mesh can be, triangles of varying size. It can also be other shapes as long as it tiles properly. And in this case, it's nice because you can have an adaptive size so that more complex areas have smaller triangles to be able to better describe them, whereas larger, more uniform areas can have larger triangles, so that you're reducing computational costs. And these triangles basically represent different physical aspects of the material. Right? Again, just like with the tornado forecasting, using finer meshes can lead to more accurate modeling to describe more complex regions, but this all comes at the cost of computational, a higher computational cost, right? But in both of these cases, you are decomposing your problem into parts that can be solved in parallel. And this is a key feature and requirement really to take advantage of any HPC environment these days. And this can scale up to billions or even higher of mesh points as done with this entire aircraft here. Another example is drug design. I come from computational chemistry background, so this is near and dear to my heart. Many drugs work like a key and a lock, right? So you have your key, which would be the drug, and then your protein is the lock. And you essentially want to have the small molecule bind to the surface of the protein, which either has the protein express its function or it suppresses the function of the protein. Right? And just like a lock picker might try many keys to find a good fit, right? Basically, we can do the same thing with drug design. So you can have a whole library of many small molecules, and you just try them all and see what works, right? So it's not uncommon for libraries to be composed of billions of molecules, and then they try, hundreds or even thousands of different positions across the surface of the protein looking for good fits. And so they basically just try different spaces all over the surface of the protein looking for good fits to come up with what's called a pharmacophore, which is kind of a precursor to a drug that will enter development. Okay, and ray tracing. So if you've seen any movie or TV show that has any imagery in it that's not real today, it is ray traced, right? And so the way this happens is you set up your three-dimensional scene, and essentially there's a fictional light source outside of the scene, and there's a fictional viewer looking at the scene, and the light, they basically trace the ray of light coming out of the light source, bouncing off of elements inside of the scene until it eventually leaves the scene and enters the viewer's eye, right? And so the scene that we see here in this picture is what the fictional viewer would be seeing, right? And the different aspects of the objects in the scene can be have different physical characteristics, and that changes how the light interacts with them inside the scene, right? And so you can see that if you have like a TV show or a movie, you start to have hundreds of thousands of frames, And each rendering just a single frame can take many hours to do. And so some of the largest HPC systems or private HPC systems are the likes of DreamWorks and Disney, expressly for ray tracing movies as quickly as possible so that the artist can iterate as quickly as possible. Okay, so let's talk about ManeFrame II specifically. So M2 features state-of-the-art CPUs, accelerators, advanced networking technologies, a substantial amount of memory per node, and we also have interactive GPU accelerator remote desktops that are available to users. M2 runs the CentOS 7 Linux operating system, which is a Red Hat Enterprise Linux derivative. So for those that have used that kind of system or any other Linux operating system, this should feel familiar. And if not, we have a nice tutorial at the M2 documentation page to cover the basics of working at the command line, the Linux command line. We use the Slurm resource scheduler and the LMOD environment module system. I specifically like to put these three together because this is kind of the trifecta of many modern clusters. So while some of the pieces we'll be talking about for the rest of the talk are specific to M2, a lot of this information can be easily abstracted and is applicable to other clusters around the world because many use CentOS, Slurm, and LMOD as the basis for their clusters. We have many development tool chains to choose from. So if you are doing C, C++, or Fortran development, we have many versions of GCC, LLVM, Intel, and PGI compilers with their associated performance libraries and MPI as well. And then if you're doing higher level programming using the likes of MATLAB, Python, and R, we have various versions of that as well. M2 is what we call a heterogeneous cluster, meaning that it has many different node types, right? And so the kind of two biggest delineations that you can make between the nodes is the amount of memory that it has and whether or not it has a GPU accelerator associated with it, right? So you can see here that the standard memory node and the medium memory node, the biggest difference there is that it goes from 256 gigs of RAM to 768. And then for the high memory, it doubles again to 1.5 terabytes. And I like to point out that this is actual system memory or RAM, not hard drive space. So I get that question a lot, whether these numbers are actually correct. Yes, so your laptop may have 8 or 16 gigs of RAM. The lowest amount that we have on any node of M2 is 256 gigs. So substantially higher than you're likely to have on your own local machine. And a lot of cores, right? 36 cores, 24 cores, 40 cores available to your application. We also have a number of GPU nodes. So the GPU1, the node itself is identical to our standard memory node, but in addition to having a NVIDIA P100 GPU. These are extremely high-end GPUs from NVIDIA that are geared explicitly for computation, right? So these aren't for 3D graphics or rendering or that sort of thing. They are very good at linear algebra type operations. And today, many applications have native support for NVIDIA GPUs. So depending on the application that you're using, there's a good chance that you can take advantage of this, this compute capability. We also have several new nodes, the V100x8. These have 36 Skylake cores, so newer than the other nodes, 768 gigs of RAM each, and 8 NVIDIA V100s. So up until very recently, the V100 was the newest, the most high-end GPU that NVIDIA offered. They recently just came out with the A100, but the V100 is an extremely fast GPU, which can give extreme performance for double precision workloads all the way down to half precision workloads if you're doing kind of machine learning type applications. We also have a lot of storage, right? So we have our scratch space, which is nearly 3 petabytes of usable space. And so we can host very large data sets depending on your needs. So M2 is housed in the University Data Center, or the UDC. This building is designed as a lights out facility. So no one actually has a permanent office there, though people are coming and going all the time to work on M2 and other servers that are housed in this location. So here they are building M2. So you have the individual servers go into racks that are, you can see there. And the nodes themselves are basically the size of large pizza boxes. And they just slide in into the rack space and are hooked up in the back for networking and power. SMU does what's called hot aisle containment. And so you can see in this picture, there's kind of a grating in the floor, and cool air comes up out of the floor, is pulled in by the fans of the machines into the center aisle, where it's exhausted out the ceiling, and then recycled. It's recooled, and that cycle repeats. And it's an efficient way to handle all of the heat that's generated by the machines when they're running. On top of the UDC, there's a number of very large air conditioning units to do all that cooling that we just mentioned. And it also has a gas generator. So the facility has enough battery backup to run for a number of minutes so that this machine, the generator, can get up and running. So speaking of tornadoes and storms, if you happen to be working on M2 and during a storm and your power goes out, you might lose your connection to M2, but you can rest assured that M2 itself is still running along with your calculations. So it can just keep on going without having external power. Okay, so a brief introduction to accessing M2. So there are 2 primary ways you can access M2. The first is using SSH, which stands for Secure Shell, and the HPC Portal, right? So kind of traditional usage and power users will readily use SSH. This provides command line access to our login nodes. And from there, you can launch jobs on the system, right? You can also run graphical applications via SSH using X11 forwarding. And this just requires having an X11 client on your local machine. There are X11 clients for all the major operating systems. So Linux, macOS, and Windows all can have X11 installed. So you can run graphical applications that way. M2 has 5 login nodes that are all accessible via m2.smu.edu. So you don't need to pick a specific one. You will be dynamically allocated to one of them. And it doesn't matter which one you're on. They all are identical to each other. The HVC Portal is a new interface for as of this year that allows users to have web-based access to M2 resources. It has a web-based SSH client, which is nice. So if you happen to be, for example, on Windows, which doesn't have a native SSH client, you can just point your browser to hvc.smu.edu, and you can get access that way as well. Via the portal, you also have access to Jupyter Lab or Jupyter Notebooks for Python development mostly, though Jupyter can support a number of other languages as well. RStudio for our development, and remote desktops for doing interactive graphics on M2. So for SSH and X11, for Unix or Unix-like operating systems, Linux, or any of the BSDs that are out there, essentially they all have SSH and X11 installed by default. So you don't need to do anything. You just need to open your terminal application, and you're good to go. For macOS, macOS is a Unix operating system, so it does come with an SSH client installed by default. It does have a terminal app by default. Apple does not use X11 natively for window compositing, so but they do support the Xquartz project, which is X11 on top of that. And so you can just go to xquartz.org and download the latest version of the X11 that they provide there. But that's just a one-time install. It's quite simple. And then you have X11 on your Mac. For Windows, Windows is not a Unix-like operating system, and so a lot of these standard utilities are not available. But there are a plethora of SSH clients available to you. Most people use PuTTY, which is a free client. But there are others as well, and depending on your preferences, you might have one that you prefer. As long as it supports SSH, you are good to go. So you can use PuTTY or WinSCP or TerraTerm. There are several others that are common as well. Most people use Xming for X11. Again, it's a free download and installation. And the instructions for doing all of this can be found at the M2 documentation site. Within Windows, there are a couple of Unix-like emulated environments. Ubuntu for Windows, which is called WSL2 now, kind of a lot of changing names, but it's essentially the same thing. But this is a really nice feature of Windows 10. So if you have a new version of Windows 10 or kind of the latest version, it allows you to have a Linux environment right on your desktop there. And it works really well. And so you can basically use it as if it's a Linux client. It does not provide X11 by default at the moment, but it can be set up to use Xming. There's also Cygwin, which a lot of people use, which can provide SSH and X11 as well. So lots of options. For transferring files back and forth, the main key that you need to take away is it needs to be an SFPP client. There are a number of these available. For macOS, you can do CyberDuck or Transmit. CyberDuck is free and Transmit is not. For Windows, most people tend to use either WinSCP or CyberDuck. Again, both of those are free. And certainly, if you're in a Unix-like environment, you have lots of command line options available to you for transferring files back and forth. Note that, just to reiterate, it really needs to be SFTP. There is a protocol called FTPS, and those are not the same. So the S needs to be at the beginning, which is basically FTP masquerading as SSH, and that works fine. And generally, when you're using one of these clients, it presents you with two panes. And you can just drag and drop files back and forth between your local machine and M2. So it's quite easy to transfer files back and forth. The portal, which can be found at hpc.smu.edu, provides an integrated and single access point for accessing a lot of HPC resources. To access the portal, you just need to have an M2 account, which you can request at smu.edu/crc. And then once you have the account set up, you can go to hpc.smu.edu and sign in with your SMU ID and your password. And it just uses standard SMU login and dual authentication to get in. Note that it is your SMU ID and password. And when you're logging in using SSH M2, that is your your M2 username and password. So different credentials there. but same password across the board. So accessing application and tools once you're on the system. So we have a lot of software installed on M2, various versions of different applications, and these are all provided by the module system that we use. So I won't go through all of these commands that you can do, but to see what is available, you can do module avail, and that will provide the list that we just looked at in the previous slide. And then to load something, you can do module load and then the name of what you want. So example, Python, or module load MATLAB to load the latest version of MATLAB into your environment. I will mention module purge. It's probably my favorite command. So if you ever have a setup and you're not sure why something is the way it is, you can unload everything with module purge. So it's kind of like a reset. So I like to point that out as a good way to go back to the beginning. Submitting jobs using Slurm. So there are a number of classes of applications, and most applications that people are running on M2 fall into one of these kind of general classes, right? So serial, shared memory, and distributed memory, right? So serial calculations are usually short-lived, single-threaded calculations, and it's not uncommon to see these run in batches. And these batches can be large, right? So they can be hundreds or thousands or even millions of individual tasks run, but each task itself is quite short and is doing nothing in parallel by itself. And you can certainly submit these individually, or you can use Slurm's array feature, which can bundle them together. And you can also bundle them onto a specific node, right? So there's a myriad of ways you can submit very large numbers of jobs all at once. Right? So this is great if you're doing kind of Monte Carlo type work, or looking at a data set and looking that has some sort of repetition to it, that you can do the same amount of work on various aspects of the data. So shared memory, these jobs are usually longer lived and more computationally intensive jobs, usually with higher memory requirements, right? It is not uncommon to see days, weeks, or months required for these jobs to complete, right? And so we have nodes set aside for this kind of use case. And then distributed memory. These are generally the most computationally intensive jobs, and they can span nodes, right? So you have a single application running across multiple nodes, utilizing all the cores and resources available to it. It is not uncommon to see many nodes allocated to a single job. So how are resources managed on M2, right? So M2 is a compute resource that's shared by all the users. And we use a queue system to manage access to specific resources, right? So if you have used another HPC system before, you may be familiar with other queue systems that are around. There's some listed there. M2 uses Slurm, which stands for Simple Linux Utility for Resource Management. So generally, allocation is governed by what we call the fair share factor. And this has two major components. One, preference is given to those who have submitted the fewest number of jobs, right? And the reason for this is to prevent a single user from blocking jobs of others, right? So if someone submits 1,000 jobs, the next user doesn't have to wait for all 1,000 of those jobs to complete. So you'll end up with being able to basically jump in front of the line, like so. And this is a balancing act between how many jobs you've submitted in a short period of time and the share fair factor getting worse the more jobs you submit, right? And then over time, it'll improve again. I usually tell users to not worry too much about what their share fare factor is. You should use M2 to get the jobs done that you need to get done, and not worry too much about how submitting jobs are going to affect your share fare factor. Right?
I would imagine mine is terrible.
Yeah. Allocations can be requested interactively or as a batch job. So interactive means that you want to sit and wait for the allocation right away and then use it interactively while you have it. And then when you're done, it goes away. Or as a batch job where you basically tell Slurm how to run your job at some point in the future. So you submit it to the queue and it will wait. And then when the resource becomes available, it'll run, even if that's in the middle of the night or the next day or something like that. It'll just run as soon as the resource is available. We use queues or partitions. You can use those words interchangeably to distinguish between resource types and the maximum runtime of your job. So these queues here, the two major parts of it are the node type, which we already discussed, mainly how much memory it has and whether or not it has a GPU associated with it. And then the other part is the duration. So these durations are hard to limit. So I usually like to say that, for example, if you use standard mem-s, which you can have an allocation for up to 24 hours, if your job wanted to run for 24 hours and 1 minute, it did not finish because it was forcibly killed at one day. So it's good to have an understanding of how long your job will run, given the resources that you're giving it, right? I'm commonly asked, well, how do I know? And that's a great question. And so the best way is just to test, right? Start with a small data set or a subset of your data and see how long it takes, and then give it a little more data and see how long it takes. And usually you can then kind of plot a line basically and see how long the full data set or the full fidelity of your calculation is going to take to run. And certainly don't hesitate to reach out to myself or Eric if you have questions about kind of how to get started with this or how long you think it's going to take or the best resources to use for your specific application. Slurm only has a few commands associated with it. Again, I won't go into too much detail about this. You can look into our past workshops and documentation that are at the M2 documentation site. But two things that I'll point out. SQ-U and your username shows your jobs that you have running. So this is probably the most important command for people to be able to see what jobs they're running. And then sbatch and srun for batch jobs and interactive jobs, respectively. Okay, so certainly if you need help or have any additional questions, please don't hesitate to reach out to me. I'm at rkalesky@smu.edu, and Eric is at egodat@smu.edu, and we'd be glad to help you out getting up and running on M2, or if you have specific questions about your applications and data set, glad to help you out. And now we'll go through a demo. Eric will give a demo of the Open On Demand HPC portal.
Let me just switch my windows here. Okay. So I started off, this is our Center for Research Computing homepage, because the demo I'm going to do if you want to follow along at home, you'll need an M2 account first. So you can go to just either Google SMU CRC for the Center for Research Computing. It's also nested under the Office of the Provost. So here we have, as Rob mentioned, some information about M2 and our documentation and our workshop schedule. Hasn't quite been updated yet for the fall, but that'll be coming soon. And here you can request an account. So if you're faculty and staff, you can just fill out an account. And here, if you're a student, you'll need some sort of advisor or supervisor or sponsor. And if you're a faculty member wanting your entire class to have an M2 account, so say you want to use the portal to teach, say, text mining, and you want everybody to have a standard environment, this is a great tool for doing that. And you'll just need to fill out the new account form and then upload some information about your class so that we can create accounts for all of your students. If you have any questions with that, just either send us a message or shoot us an email via the help desk and just say M2 accounts, and it'll trickle its way to us. So once you have an account, if you're interested in using this, you can go to hpc.smu.edu, and it'll look like this. It'll first actually make you sign in with your credentials and make you do Duo. We've skipped that part. And so now you're actually not quite inside M2 yet, but this is kind of a nice on-ramp if you're not comfortable using a command line system. You still have access to all of the command line features. You can do a terminal just like you would, and this is, you can see this is my login. I'm on login node 3. That was, again, dynamically allocated. And we have how many jobs and are running and idle and waiting in different queues. Our message of the day is tucked somewhere in here, I think. And so we can do all of the normal command line commands we would do, just as though we were in a regular terminal on an SSH login to M2 or on your own Linux machine or Mac or command prompt in Windows. Similar environment that way. But where the portal can really take off is we have things called interactive apps. So first one I'm going to show you is the one nearest and dearest to my heart. We can use Jupyter Lab, which I have a custom environment here, but you can use some just standard environments. We'll notice we picked a queue and some specifications, and Rob and I are happy to help any users who have questions about all of this get set up, or if they have you need a custom environment set up, we can talk to you about how to do that. So we'll click launch, and it'll take a second while the job is being queued, because what that launch button did is actually submit a job to M2 to set up this environment on one of the compute nodes. And as I mentioned earlier, my priority is probably pretty low. So this might take a minute or two while we go. While it's doing that, we also have a remote desktop, which will go ahead and launch that one as well. And we have access to RStudio server, which if you're an R developer, RStudio is likely the IDE that you're using. And so you can use that interactively on M2. I'll go ahead and get all 3 of these started. And then we'll wait just for a second. So the portal also has some other features. You can see your active jobs, which we have all 3 of these are queued, as you can see here. And you can do some basic job management. You can cancel your jobs and things here. We also have MATLAB and SAS, if you're interested in either one of those. Okay, our Jupyter Lab job launched. We have, it remembers where we were last time. So you can see here, this is, there we go. Normally it would launch and look like this, where you have your Python 3 notebooks, consoles, and some other options. You can do a terminal this way. You can do a text file and some other things like that. All of the folders here would be what it looks like in your normal M2 home directory in this nice navigation tool. So we can open a Python notebook, maybe. Running a little slow today. There we go. And so we have a full set of interactive cells, just like we have in Python, or in a regular Python notebook you would run on your own, running Python code. We can also launch a new notebook and just start doing kind of whatever we would want. And run our code. So going back to the portal, we have the ability to launch a remote desktop. And what the remote desktop will let you do is use tools that you would normally need a graphical interface for. So a good example is VMD. And so I use the module load command that Rob mentioned earlier. And then I should be able to run VMD. And we should get the graphical interface. Here we go. We use VMD for this demo because eventually this VMD, there we go, will start spinning. And so that's something that you wouldn't normally get from the command line, or that might be a little slow via X11 forwarding. And so the virtual desktop is a good development environment for that. And then I'll just briefly touch on our studio server, maybe. Doesn't seem like it's loading quite yet, but we can also, let me open a new terminal, and do, just like we had MATLAB as an interactive app, you can run MATLAB, if I can spell MATLAB. You can run MATLAB from within the virtual desktop as well. So again, if you're trying to teach a class and you don't want all of your remote students having to have their own instance of MATLAB on their own machines, or you're tired of debugging everyone's individual installations, you can use a standard tool set where everyone is working from the same base operating system. And R does run. Rob, do you have any idea why it hasn't started yet? That would be why.
Or go to development and set the hours to 1. Yeah.
So I had a typo, so that should kill this one off. So what I had done there is mismatched the requirements for a queue with the specifications I had asked, and now we're starting just fine.
It's also good to mention that all of these interactive sessions that you have running, you can like close your browser, turn off your laptop, and then reconnect to them later. And they'll still be running on M2. So for example, this RStudio session, you can get a job going and then close the browser tab and come back to it later, and it'll still be there.
Yep. And I actually don't know if I have any R files, but this is the full RStudio instance you would expect. We have different versions of R available, but so if you need a different one than what's by default. You'll have to talk to us about how to do that. And then that's pretty much it. Rob, did I miss anything in the terminal or in the portal?
If you go to Files at the top,
Oh, right.
yeah, you can, it's a nice way to have access to your files on M2, and you can upload and download files from M2 that way as well, without having to install a specific SFPP client.
Right. Another useful feature is if you're using Jupyter Lab, you can actually download files directly to your desk or to your computer, just as you would from any web-based tool. Yep. And so with that, if you have any questions about using any of the M2 portal or tools, again, reach out to Rob and I, either via the help desk, or you can reach out to our personal emails. We're happy to get you and your class set up using these tools. And thanks for sitting through this with us.
Thanks so much.